Hello, welcome to my lecture on magnetostatics. This is a lecture for my SEM 2 student. Till now we had been calculating the potential and the field due to a current carrying loop, and I have shown that the corresponding magnetic field turns out to be similar or to be analogous to that of an electric dipole. So we can assume that a magnetic dipole is nothing but equivalent to a current loop. Okay, I would like to further go on for calculating the magnetic field, rather magnetic torque on a current carrying loop. That is the topic. Today's topic is calculation of the force and the torque on a current carrying loop or on a magnetic dipole. So let us try to force and torque acting on a magnetic dipole oblique current loop. This should be, they are equivalent. A magnetic dipole is equivalent to a current carrying loop. So let us try to evaluate that. Suppose we have a current carrying loop which can be of any arbitrary shape, which has a current I flowing through this. We have an elementary length dl. So if it is placed in an external magnetic field, let's say B, which is pointed along the y-axis, so this is B is nothing but equal to B of j cap, and the normal to this particular loop is making an angle theta with the direction of the field. Let's say we have the x-axis to be along this direction, perpendicular to the y-axis, okay, and then we have z-axis also perpendicular to the xy plane. Suppose we have a current carrying loop. I want to calculate the amount of torque acting on this, and this can be evaluated by taking if the coordinate of this with respect to any arbitrary origin be r prime, then we can always take r prime cross, if this is an elementary length, I dl cross b, because this is the amount of force acting df. So we can say, so what is the net torque acting on this on this whole of loop? Now that would be equal to r prime cross I dl cross b. Okay, so we would try to see what is the value of this. Now this loop element, this big loop, can be divided into a large number of small square loops. If I again take the same loop carrying the current I for the elementary length dl, and I divide this into a large number of square small loops, each of side A, then we can always cancel out the direction of the direction of the current. We can just cancel out the current as we did in the case of vector analysis. We had divided the whole area of the loop into a large number of small square loops, and we can always cancel out the common side for two adjacent squares, and then effective current flowing through the total area of the loop. The area of the loop would be the same as that due to the addition of all those individual elementary square loops. So we can replace the above picture by a square loop of side A. Let's say a side A, which is again making an angle, the normal to this is making an angle theta. This is again the y-axis, so this is B j cap, this is x-axis, and this is z-axis. Okay, so if I want to calculate the amount of, and this is carrying a certain amount of current through this, which is I. Okay, and this is an elementary square loop, and you have so many such elementary square loops which actually make this whole complete loop, and we want to find the amount of torque acting on that particular loop in the presence of a current carrying loop, in the presence of the external magnetic field. So let us try to first of all calculate the amount of the torque which is acting upon this elementary square loop of side A. This square loop is also carrying the same amount of current as I, and the sides are A. Now we can see that this PQRS square loop, which is carrying a certain amount of current, then the sides PQ and RS, the amount of torque acting is given by, if we want to say what is the amount of torque acting, or what is the amount of force due to this, that would be equal to I times A. A is along the, let's say A is along a particular direction in the xy plane. Then the force acting on the side PQ and RS would be equal and opposite, and they would be acting along the same line which is parallel to the z-axis, and they tend to cancel each other. So the force on the element PQ and RS are equal and opposite and act along the same line, that is the z-axis. So net force equal and opposite, and they tend to make it 0. So no effective torque is acting due to the sides PQ and RS. But if you again talk about the sides SP or PS and RQ, then again there are two forces equal and opposite acting. So if I just write RS, okay, if I draw RS like this, RS, okay, and then the magnetic field is along this B, along the y-axis, which is making an angle theta. This is my n cap, the same picture. And now along RS, if what is the amount of torque acting, that would be, or what is the amount of force acting, that would be equal to, if I say that it is along the x-axis, if this is parallel to the x-axis, then we can write the force acting to be equal to force on RS is equal to I of A, and this is along the minus of x-axis because this is along the negative x-axis, cross B of j cap. Same fashion we can say force on PQ is IA of plus I cap cross B j cap, and we can write this as equal to IAB and this is along the minus of I cross j is minus of k cap. So minus of k cap, and this is I a b plus of k cap. But now the force are again equal and opposite, but now they are acting not along the same line, but one is acting along the line PS and the other one is acting along the line RQ. So one force would be directed along this and the other force would be directed along this, and they are separated by a distance A. So now we can talk about a torque acting, and that torque tau would be equal to A, where A cross, or rather I can say A by 2 cross this force plus A by 2 cross this force, which again makes it A. So A of I cap cross I A B of K cap. So that is going to give us a net torque of minus of K cap. Okay, so that is going to give us I A square cross B of J cap. So that torque would be along this I A square. So this is nothing but I can say I A square I cap, and I can make this as B. So this can be written as I A square, can be written as M, the magnetic moment, cross B, because the current flowing through a loop times the area gives us the magnetic moment. This is something which you can remember as torque in the case of electrostatic dipole as P cross E, where P was the electrostatic dipole moment, electric dipole moment, and E was the electric field. So we get a sense of deja vu, where one can say that the torque in the case of electrostatics was P cross E, and here in the case of magnetostatics becomes M cross B. Now every dipole has a potential energy. Every dipole in the presence of external magnetic field has a potential energy associated with it, and if we know the amount of the torque, then from the expression, as we know the amount of the torque which we had derived already, tau is equal to M cross B, where M is the magnetic moment and B is the corresponding magnetic field in which the magnetic dipole or a current carrying loop is placed. Then we can always calculate the corresponding potential energy U as equal to, or du to be equal to tau d theta. If I call this as mb sine theta, the magnitude of tau, okay, because whenever you have a magnetic dipole and it is oriented along a particular direction, let's say this was my magnetic dipole M, okay, and this was my magnetic field making an angle theta, then we can say that for moving it to a certain amount along the field direction by an amount d theta, the amount of potential energy which is stored with the amount of work done in rotating the magnetic dipole by an amount d theta would be equal to this, which would be stored as a potential energy within the dipole. So that's why we are writing this as tau d theta. So we can write this as mb sine theta d theta. So u would be equal to integration of mb sine theta d theta from some initial position theta 0 to theta. So you can always integrate that mb of minus cos theta from theta 0 to theta, which makes it as mb of cos theta 0 minus cos theta. And if for the special case for theta 0 the initial position be pi by 2, then you can be written as minus of mb cos theta, which is nothing but equal to in vector form m dot b, similar to that of again the electrostatic potential. In the case of electrostatic, the potential energy was minus of P dot E, where P was the electrostatic dipole moment and E was the electrostatic field. Similarly, we get minus of M dot B as the potential energy associated with a dipole. If it was initially present along the perpendicular direction, and then you have to move it so that it would align itself along the direction of the field, and then the corresponding potential energy stored within that particular dipole would be equal to minus of m dot b. Now, what is the force acting on the dipole? The force can be treated as F is nothing but negative gradient of the potential energy, as we know that. So this can be called as gradient of m dot b. So we know from vector analysis that gradient of a dot b can be written as b dot del into m plus m dot del into b plus b cross curl of m plus m cross curl of b. This is the expression. Now for constant m, for a given m to be fixed, we can, first term would be 0, gradient operating on curl of m would be 0, and if curl free b for magnetic dipole, curl of B is also equal to 0, so that makes the force acting on the magnetic dipole to be equal to m dot del into B, which is again equal to, you can again remember for electrostatic case, this was for electrostatics. Here also again we are remembering the electrostatic case which you have studied, as equal to P dot del into E. So this is the amount of force acting on a magnetic dipole which we have derived. So this is the force, and the corresponding torque acting for a magnetic dipole is this. In our next lecture, we would be studying the magnetic property of materials. Thank you.